We're looking at the Honors Math 2 second semester final. We're looking at Chapter 7b. So we start with our portion of our unit circle. We need to figure out some ratios before we get on to simplifying other things. We start here, we have cosine theta we need to find for its common angles in quadrant 1. Now cosine is the x value in the coordinates. You can also go back to using your special right triangles and finding the values, but for this let's just look at x values. At 0, cosine is 1. At pi over 6, it's root 3 over 2. Pi over 4, it's root 2 over 2. At pi over 3, it's 1/2. And at 90 degrees, or pi over 2, it is 0. Sine would be the y value. So sine, the y value starts at 0, then 1/2, root 2 over 2, root 3 over 2, and 1. Tangent is sine over cosine, so that would be the y value over the x. So I get 0 over 1, which is 0. We get 1/2 over root 3 over 2, which becomes 1 over root 3, which is root 3 over 3. Root 2 over root 2 over 2 is 1. We get root 3 over 2 over 1/2 is just root 3 over 1, or root 3. And then 1 over 0 is undefined. Secant is the reciprocal of cosine, so we're going to do the reciprocal of 1 is 1. 2 over root 3 becomes 2 root 3 over 3. Root 2 over 2 becomes 2 over root 2, which is then going to be just root 2. Reciprocal of 1/2 is going to be 2, and then the reciprocal of 0 is undefined. For cosecant, that's the reciprocal of sine, so that starts out with undefined. Then we go 2, root 2, and 2 root 3 over 3. And that's from taking the reciprocals of here. It's the same pattern as the ones we had here, they're just reversed, if we notice that. And then last, your reciprocal of 1 is 1. This should not be secant, this should be cotangent theta. Cotangent theta, reciprocal of tangent is undefined. Reciprocal of root 3 over 3 is root 3. Reciprocal of 1 is 1. Reciprocal of root 3 is root 3 over 3. And the reciprocal of undefined is 0. So it kind of warms us up for going through and solving with our different values. I also have a unit circle that I can go through and reference them as I solve. So let's start with converting radians to degrees, or degrees to radians. 210. I want this in radians, so I like to think if I want to add in radians, change it to radians, I'm going to need to bring in a pi. So we're going to go pi over 180 is our rule. We get 210 over 180 becomes 21 over 18 once the zeros are gone. And then 21 and 18, you can divide both by 3. You get 7 and 6. So we're going to go 7 pi over 6. Negative 375 is going to be negative 375 times pi over 180. I'm going to divide both of those by 5. 375 divided by 5 is 75, and 180 divided by 5 is 36. So I get negative 75 pi over 36, but those are still, we can still reduce that. You can divide those both by 3, and then we get negative 25 pi over 12. Now for number 4, we have 3 pi over 5. We need to multiply that by 180 over pi. So the pi's then divide out. I can divide 180 by 5 and reduce that, and I get 36 on the top. 36 times 3 gives me 108 degrees. For number 5, negative 17 pi over 12, multiply by 180 over pi. 180 and 12, we can divide by 12, and we get 15 on top. So now it's going to be a negative 17 times 15, which is negative 255, which you could then, if you wanted to find the other angle, add 360 to that. And that actually also comes out to be 105, which really more applies to coterminal angles, which is the next part. So give 2 coterminal angles for the given angle. Anytime I want a coterminal angle, I can add 2 pi or subtract 2 pi. So if I have 7 pi over 3 and I wanted to add 2 pi, I'm going to add 6 pi over 3 because that's 2 pi disguised with a common denominator. So this gives me 13 pi over 3 as one option. The other way I could go is subtract 2 pi, which is going to be subtract 6 pi over 3, which leaves me with just pi over 3. So these two are both coterminal angles, and probably the most common ones we would see there. 17 pi over 6, I'm going to add 12 pi over 6 to that, because I'm going to add 2 pi. We get 29 pi over 6. Could take the same thing and subtract 12 pi over 6, and we get 5 pi over 6. Both of those are coterminal angles. You could even go further and subtract another 12 pi over 6 and write negative 7 pi over 6 for an answer. Okay, moving down, we're going to start evaluating our trig ratios. Number 8, sine of 4 pi over 3. 4 pi over 3 is in the third quadrant. It is pi over 3 past 180. We know pi over 3 is 60 degrees. In a 30, 60, 90, we go 1, root 3, and 2, with these two values being negative. So sine in this situation would be negative root 3 over 2. Cosine for 3 pi over 2. 3 pi over 2 is down here. That is at the bottom. That is going to be a 0, negative 1. As we mentioned earlier, cosine is the x value, so that is just going to be equal to 0. Cosecant of pi over 3. Pi over 3 is in the first quadrant. That is 60 degrees. We'll fill in our 30, 60, 90. 1, root 3, and 2. Cosecant is the reciprocal of sine, so that means cosecant is going to be the hypotenuse over the opposite, which will be 2 over root 3, or 2 root 3 over 3. Tangent of 7 pi over excuse me. Tangent of 7 pi over 6 will be a pi over 6 past pi. That's 30 degrees, so we go 1, root 3, and 2, with those two values being negative. We want tangent, which is opposite over adjacent, so that would be negative 1 over negative root 3. It becomes positive, you move the radical up, and it is root 3 over 3. Cotangent of negative 2 pi over 3 goes this way. It is pi over 3 short on the bottom side of reaching pi. Pi over 3 is 60 degrees. So this is just like number 8. We get negative root 3, negative 1, and 2. But now we want cotangent. Tangent's sine over cosine. Cotangent is cosine over sine, which would be the x over the y. So that's going to be negative 1 over negative root 3, or positive root 3 over 3. Secant of pi over 6. Pi over 6 is in the first quadrant. That is 30 degrees. We'll go 1, root 3, and 2. Secant is the reciprocal of cosine, so it is going to be the hypotenuse over the adjacent. So that will be 2 over root 3, which becomes 2 root 3 over 3. Cosine of 0, if we look at the coordinate, at 0 our coordinate is 1, 0. Cosine is x, so the answer is 1. Tangent of 225. 225 is past 180. How much past 180? Well, it's 45 past 180. So we get a 45, 45, 90. I fill in my parts. I have negative 1, and root 2. Tangent would then be negative 1 over negative 1, or positive 1. Cotangent of negative 150 starts in the negative direction. It stops 30 degrees short of 180. Then we could go negative 1, negative root 3, and 2. Cotangent is adjacent over opposite, so that'll be negative root 3 over negative 1, or just root 3. Cotangent of 180. 180 is the coordinate over here. That's going to be negative 1, 0. Cotangent is the reciprocal of tangent. Tangent's opposite over adjacent, so it is adjacent over opposite, which would be x over y. So that'd be negative 1 over 0. So cotangent in this case would be undefined. Sine of 5 pi. Now 5 pi would go pi, 2 pi, 3 pi, 4 pi, 5 pi would end over here. That's the coterminal to where it ends, negative 1, 0. Sine is the y value, so your answer is 0. For cosine 3 pi over 4 times sine of 3 pi over 4, I'm going to think of where 3 pi over 4 is. That is over in quadrant 2. It is a 45, 45, 90, so we can label those parts right here. So cosine of that would be adjacent over hypotenuse, which is negative 1 over root 2, times opposite over hypotenuse, which would be 1 over root 2. When I multiply this out, I get a negative 1 on top. Root 2 over root 2 is 2, so it is negative 1/2. Same thing, tangent of 3 pi over 4, cotangent of 3 pi over 4. Let's just steal the drawing I had here. Tangent is going to be opposite over hypotenuse, so that is 1 over root 2. Sorry, 1 over opposite over adjacent, so that's 1 over negative 1. Try that again. Cotangent is adjacent over opposite, so that would be negative 1 over 1. We're multiplying. Looks like we get 1 times negative 1, negative 1 times 1. The answer is 1, which we also see often. Pi over 2, sine of pi over 2. Pi over 2 is 90 degrees, so that is 0, 1. Sine is the y value, so it's 1. Cosine is the x value, it's 0, and the answer is 1. Number 5, what is the length of one period of the function of 5 cosecant 3x? So our period is equal to 2 pi over b. b here is 3, so that's 2 pi over 3. So we'd say that our period is equal to 2 pi over 3. What is the length of one period of the function of secant of pi over 5x? So we'll go period equals 2 pi over b. b is pi over 5. So that's 2 pi divided by pi over 5, which becomes 2 pi times 5 over pi. The pi's reduce out, divide out, we get 2 times 5, and our answer is 10. So our period is 10 units. It is not 10 pi, it is just 10 units. Number 9, where does the 0 occur on the function cosine pi over 5? So my period is going to be 2 pi over b, which is 2 pi over 5, which we'd say is 2 pi divided by pi over 5, or 2 pi times 5 over pi. This comes out to be 10. So I'm going to go to cosine. I have, there's the cosine period. Keeps going if we needed to. We know it finishes one period at 10. Our 3 steps are the 0, minimum, and 0. So that's going to be 5. That's going to be 5 halves, or 2.5. And this is going to be 15 halves, or 7.5. So it looks like our zeros are at 5 over 2 and 15 over 2. Now if we went through and predicted where the next one was, if this was 2.5, 7.5, I see I added 5, 12.5 is actually our next one, which would be 25 over 2 as well, and we could keep listing them on. It likely just wants one period, so we would indicate those 2 points. Now if it wants it as a coordinate, we'd say 5 over 2, 0, 15 over 2, 0. So if we need to name 3 asymptotes of y equals 3 cosecant x, we first need to graph the function. Now cosecant is the reciprocal of sine, so I'm going to graph a dotted sine curve here. And in this case the amplitude is 3, so we have 3 and negative 3. Not really necessary to the problem. We know the period is going to end at 2 pi. And 4 pi would be the second end of the second period. Half of 2 pi is pi. Half of that is pi over 2. Halfway between those is 3 pi over 2. We could also mark 3 pi, 5 pi over 2, and then eventually 7 pi over 2. So this is our graph of 3 sine x. We do that to get to cosecant. Now cosecant is going to have asymptotes anywhere sine hits 0. So I'm just going to draw vertical lines in there. And now we can come in and draw 3 cosecant x. And so now the asymptotes are going to be pi, 2 pi, 3 pi, and it looks like it's going to be any integer. Pi is where those asymptotes will occur. For y equals 3 over 2 cosine pi over 2x, or pi x over 2, I'm going to put that the amplitude is 3/2. The period is 2 pi over b, which is 2 pi over 2, which is 2 pi divided by pi over 2, which we get 2 pi times 2 over pi, and it comes out to be 4. So period is 4, amplitude is 3 over 2. For number 13, negative sine of 2x over 5. Your amplitude, we're not going to say it's 1. The amplitude in this case is positive 1. That's not the negative, because I have a negative 1 there. It's a positive 1. That's still the distance from the kind of center axis up to the top. So that's 1. Period. We're going to do 2 pi divided by 2/5. So that's 2 pi divided by 2/5. Then we get 2 pi times 5 over 2, which comes out to be 5 pi for the period. Number 14, sketch 2 periods of 2 cosecant 2x. So before I do that, I'm going to graph 2 sine of 2x, which is going to have a period of 2 pi over 2, or pi. And I know sine starts at 0. There are periods. So if this is pi, this is 2 pi. That's my second period. Half of pi is pi over 2. Then I have pi over 4, 3 pi over 4. Halfway between these two is going to be 3 pi over 2. This would be 5 pi over 4 and 7 pi over 4, which are actually the 45-degree markings that we had whenever we did the unit circle, so maybe those fractions start to look a little bit familiar. We have a 2 and a negative 2 here. So anywhere we have a 0, we're going to draw in a vertical asymptote. And then our graph would look like this. And this is cosecant in blue. Okay, next we have secant of, or negative secant of 2 pi x. So we're first going to look at negative cosine of 2 pi x. The period there is going to be 2 pi divided by 2 pi, which is 1. So we have cosine, and it's negative, so it starts at the minimum. And this ends at 2 because our period is 1. So then we have 1/2, 1/4, 3/4. This would be 3/2, 5/4, and 7/4, which are actually the same fractions as the previous problem, but in this case there's no pi on it. So here's our cosine. We got a negative 1, positive 1 there. Let's draw in the asymptotes. We have graph going down, going up, facing down, facing up, facing down. So number 18, we need to write the equation for what we already have, but it's not really based on its first period. Let's just say based on the interval. So what do we know? We know it starts at 0 and goes up. So it's not starting at maximum or minimum. So I'm kind of thinking it's going to be sine. 7 is where it peaks, and negative 7. So I'm thinking A is 7. I don't know if it's positive or negative yet. We'll get there. Negative 3 looks like the end of a period. So if the period is equal to 3, I could go 3 equals 2 pi over b, 3b equals 2 pi, or b equals 2 pi over 3, by kind of manipulating things around.
So really the last thing I need to know here is it a positive or negative? Now if I continued this graph on, it would go down, so from 0, so that kind of makes me think it's going to be a negative 7. So putting this all together, I get negative 7 sine of 2 pi over 3x. And that's not even looking at the interval that I have. Okay, well, let's look at 19 now. On 19, what do I notice first? I got the 4 and negative 4. So amplitude looks like 4. Could be plus or minus. Let's wait on that. It starts at a maximum. So I'm going to make that a cosine. So really we need to know the period. Now if it started here and ended here, I need to know what that point is. Well, so far I have pi over 4 and 3 pi over 4, which are actually between two zeros. But I have this middle step here. Halfway between 1/4 and 3/4 is 2/4, or pi over 2. So if that's pi over 2, and that's half of the period, the full period would end at pi. So now I can say pi is equal to 2 pi over b. We get b pi equals 2 pi, or b equals 2. Now I can kind of see my equation is going to be y equals 4 cosine of 2x. I'm going to take the positive because it starts at the maximum, and this is my equation. For number 20, find the sine curve with an amplitude of 4 and a period of 2 pi. So we first need to say the period is 2 pi. We go 2 pi equals 2 pi over b. b times 2 pi equals 2 pi by multiplying over, and we get that b is just 1. So my equation is going to be y equals, we have a sine of x, amplitude is 4, goes out in front, that's going to be 4 sine x. A cosine curve with an amplitude of 1, a period of 4, and a y-intercept of negative 1. So that means it actually has to hit down here at negative 1. So if that was my cosine curve, I would know that a is negative 1. b, we got to solve, because we know the period is 4. We'd say 2 pi over b. 4b equals 2 pi. b equals 2 pi over 4, which is pi over 2. So I put it all together, it's going to be a negative cosine of pi over 2x. For number 22, we have a cosecant curve, amplitude of 3, period of pi over 2. So let's say pi over 2 equals 2 pi over b. This becomes b times pi over 2 equals 2 pi. b times pi equals 4 pi, so b equals 4. So this one we're going to go, the amplitude is 3x, because b is 4, and we have our equation. Okay, now a cosine curve with zeros at pi over 4, 3 pi over 2, and a minimum at pi over 2, negative 2. Let's just draw a cosine curve to start. Now anything we need here, looks like it's going to be a positive. If not, we'll start over. So I have a 0 here at pi over 4. I have another 0 at 3 pi over 2, and a minimum at pi over 2. Let's put this here. Okay, well if this is pi over 4 and this is pi over 2, then this is 3 pi over 4. Maxes out at pi. So do we hit another 0 at 3 pi over 2? It doesn't look like we actually do. We're going to call this a typo, and let's just make this 3 pi over 4 as our other 0. Otherwise, it's a shift that we really don't know how to do. So I have pi over 4, 3 pi over 4 are zeros. Make sure you make that 3 pi over 4. So now we need to graph the equation. We had a positive 2, negative 2. So that's going to be a 2 cosine x. Our period is pi. Like we saw up above, when it's pi equals 2 pi over b, you get that b is 2. So y equals 2 cosine 2x. Number 25, a secant curve with asymptotes at pi over 8 and 3 pi over 8, and a y-intercept at 4. So graph secant, I'm first going to graph cosine. So this here we have asymptotes at pi over 8, 3 pi over 8, okay, and an intercept at 4. So I know in my secant it's going to be 4 secant something x. I need to figure out what that something is, what makes the period. So let's figure out where this period occurs. So if this is pi over 8 and this is 3 pi over 8, halfway between that is 2 pi over 8, which is pi over 4. Now that is actually half the length of the period, so the period will end at 2 pi over 4, or pi over 2. So now pi over 2 equals 2 pi over b, because that's the period and we need to solve for b. We get b times pi over 2 equals 2 pi. This is b times pi equals 4 pi, if I multiply the 2 over, and I get that b is now 4. If b is 4, it goes here, and we'd say that y equals 4 secant 4x. So now, cosine squared theta minus 1 looks a lot like a Pythagorean identity. We have sine squared theta plus cosine squared theta equals 1. So if I kind of got the cosine and the 1 with same side, it looks like 1 minus cosine squared theta equals sine squared theta. But that's not entirely what I want. I need these to switch signs. So if I wanted to switch signs, I could just multiply everything by -1. And this would become -1 plus cosine squared theta, or cosine squared theta minus 1. So I'm going to replace cosine squared theta minus 1 with a negative sine squared theta. Okay, number 30, I have cotangent squared theta plus 1. That is the Pythagorean identity for cosecant. So now 3 over cosecant squared theta, we could write as 3 times 1 over cosecant squared theta. Cosecant is the reciprocal of sine, so that becomes 3 sine squared theta. Number 31, actually these two are kind of jammed together. We're going to multiply them to distribute in. I get cosine. Now, you know, before we do that, let's look here. Secant squared theta, we could use the Pythagorean identity for that. But you know what, I'm going to go with distribute. So I'm going to go cosine squared x minus cosine squared x secant squared x. Cosine squared x minus cosine squared x times 1 over cosine squared x, because secant is the reciprocal, basically turns this whole thing into 1, cosine squared x minus 1, which should look familiar because we had this earlier, that cosine squared theta minus 1 is negative sine squared theta, so then we can turn that into negative sine squared theta. Now, number 33, I'm going to think factoring because I both have a sine x in both of these. I'm going to take that out of both. 1 minus cosine squared x is left inside. That is an important one because that is the Pythagorean identity for sine squared x. So then we get sine, we have 3 of them, so we say sine cubed x for 33. 35, we're going to multiply. This is actually a difference of 2 squares and becomes cosecant, weird symbol, squared minus 1, which can go to a Pythagorean identity of 1 plus cotangent squared theta equals cosecant squared theta. Well, I want to get this to be the same, so if I subtract 1 from both sides, I have the same thing, so we're going to say that it is cotangent squared theta, and that's not a fraction, that's the actual answer. Number 36, I'm going to factor out the 4s and get cosine squared theta plus sine squared theta. On the inside, this becomes a 1, so it's 4 times 1, the answer is then 4. For 37, I can factor a cosine out of both, and this leaves me with sine squared theta plus cosine squared theta, which looks pretty familiar because this turns out to be 1 times cosine theta, which is just cosine theta. For number 41, I'm going to break these into two fractions. You cannot cross out the tangent squared, so don't you dare do that. But what I can do is make this 1 over tangent squared theta plus tangent squared theta over tangent squared theta. Now 1 over tangent squared theta is cotangent. Tangent squared over tangent squared is 1. But if I had something of cotangent theta, squared theta plus 1, another Pythagorean identity, and that comes out to be cosecant squared theta. So then we get to our proofs. Now the nice thing about the proofs is they're just like the simplifying we just had, but we know the end result. So your goal in the proof is not to show me the answer that you get, it's to show me the steps to how you arrive to that answer. Show all your steps. So for something like 46, I'm going to take the more complicated side first. Cotangent theta is 1 over tangent theta times tangent squared theta. I'm going to put that together and get tangent squared theta over tangent theta. This reduces tangent squared over tangent just to be 1. Tangent theta, it comes down, we get tangent theta equals tangent theta. For number 49, I'm going to split the fraction on the right-hand side. So I'm going to make this 1 over sine x minus cosine x over sine x. Reciprocal of sine is cosecant. Cosine over sine is cotangent. And now it matches. Cosecant x minus cotangent x. For number 51, the way I approach 51 is I'm going to write them all out on the left-hand side as secant x times cosecant x times 1 over cotangent x. Now I'm going to change them all to be in terms of sine and cosine. Secant is 1 over cosine x. I have cosine x. And then cotangent is, that should be a cosecant. Reciprocal of cosecant is sine. Cotangent is tangent x, which is going to become sine x over cosine x. So now they have them all together. The sines are gone, so it's now, come over here, 1 over cosine squared x, which its reciprocal is secant. Secant squared x equals secant squared x. Last one, I'm going to work with the right-hand side. On the right-hand side, I have 1 over cosine x minus sine x cosine x over cosine x. Now cosine x is secant. This one, I'm going to divide out the cosine x's, and I'm left with sine x. So then I get secant x minus sine x for my answer.